In this case, you can observe that all the tangent lines to this curve are below the graph, or that the graph lies above its tangent lines. And in this case, you can observe that all the tangent lines of the curve are above the graph, or another way to look at that is that the graph lies below its tangent lines. Definition: the graph of a function is concave up or upward on an interval if it lies above all its tangent lines on that interval. The graph of a function is concave down or downward on an interval if it lies below all its tangent lines on that interval. Example: you can observe that this happens here. From the point A to infinity, this graph is concave up. Now you can observe that here it's concave down. And we can summarize that f is concave down on negative infinity to a, and it's concave up on a to infinity. Up, down. You can see also that f changes its concavity at x equals a. We will call the point AFA an inflection point or point of inflection, and here is the definition for that. A point P is called an inflection point or a point of inflection if the curve changes its concavity at this point. Let's see what happens even more. Here are the slope of the tangent line to the curve from negative infinity to a. And here from a to infinity. I copy the slopes down so you can see the progression. Now let's focus on this side, from negative infinity to a. If you see, the slopes of the tangent lines are decreasing. It's very steep at the beginning, and then it's even turned from positive for the first one to negative in the last one. What does it mean? It means that the first derivative is decreasing because the slope of the tangent line is the first derivative. So the function that represents the slopes of the tangent lines is decreasing, which means that the derivative of the first derivative is less than 0. But the derivative of the first derivative is the second derivative. And we get that when the slopes of the tangent lines are decreasing, the second derivative of the function has to be less than 0. But we can also observe that this happens when the graph is concave down. Now let's observe what happens when the graph is concave up between a to infinity. If you look at the slopes of the tangent lines, now it is increasing. If you look, the first one has even negative slope and the last one has a positive slope. It means that the first derivative as a function has to be increasing. And it means that the derivative of the first derivative has to be greater than 0. But this is the second derivative. So there is a connection between the second derivative and the concavity. And if what we did is true, which is true, we can also say that when the graph of the function is concave down, the second derivative is negative. And when it is concave up, the second derivative is positive. The conclusion that we had before are totally right. It's even in a theorem. Concavity test. It's a theorem that tests for concavity. If the second derivative of a function is greater than 0 on an interval, then the function is concave upward on that interval. If the second derivative is less than 0 on an interval, then the function is concave downward on that interval. Example. Let's take the function f(x) equals x cubed and let's find its concavity. We have to get the second derivative, but not before we have the first one. Here's the first and here's the second. Now we are going to do analysis on the real line for this one. It is 0 at 0, and we are going to do exactly as we did with the first derivative, but now for the second one. It is 0 and 0, and it's easy to see that when x is negative, the second derivative is negative, and when x is positive, the second derivative is positive. Using the concavity test, we see that here it is concave down and here it is concave up. We conclude that the function is concave downward on negative infinity 0 and concave upward on the interval 0 to infinity. Even more, if you remember the definition of the inflection point, you can see that at x equals 0 there is a change in concavity. So we can even figure more that the point 0f of 0, which is 0, 0, is an inflection point. Make sure that inflection point is a whole point. It's an x and y coordinate. What if the second derivative of a function equals to 0? It may or may not be an inflection point. This is exactly as critical numbers may or may not be a minimum or maximum. And I want to give you an example for that. f(x) equals x to the power of 4. Here is the first derivative and here is the second. You can easily observe that the second derivative is 0 when x equals 0 and otherwise it is positive. So the function is concave up here and concave up here. So even though that the second derivative is 0 at x equals 0, there is no inflection point at this point. The values x for which the second derivative equals to 0 are sometimes called second-order critical numbers. I'm not going to use this very often. You can observe also by looking at the graph of the function that even though that the second-order critical number is 0, there is no inflection point when x equals 0. Example. Find where the graph of the function f(x) equals x to the 4 over 4 plus x cubed over 3 plus 1 is concave up or downward and find its inflection points. It is a polynomial, it is continuous and differentiable as many times as we want. Here is the first derivative, and here is the second. We will have to write it as usual as a product of two terms in this case. And we are now going to find the zeros. This is 0 when x equals 0, and when x equals negative 2/3. And we are going to perform the analysis on the real line, but now for the second derivative. It is 0 at negative 2 over 3, and it is 0 at 0, so we have to check the sign of the second derivative on 3 subintervals. We'll take sample point as usual. We will substitute negative 1 in the second derivative, and it is a plus. Then we will take a sample point between negative 2/3 and 0. Negative 1/2 is a good one. And here we'll get negative. And then we will substitute 1 in the second derivative and we will get a positive number. This is a plus, it is concave up. This is a minus, it's concave down. This is a plus, concave up. We can see 2 times at which the function is changing its concavity. This is one of the inflection points, and this is the other. We summarize that it is concave upward on the intervals negative infinity, negative 2/3, and 0 infinity. It is concave downward on the interval between negative 2/3 and 0. We can also conclude that there are two inflection points. Be careful. Inflection point is a whole point. In the analysis, we only have the x-coordinate. For the y-coordinate, we have to substitute the x-coordinate in the function because inflection point is a point on the graph of the function f(x). f of 0 is 1, and f of negative 2/3, after you do some algebra, you get 77/81. So we can conclude that the inflection points are, first of all, 0, 1, and then negative 2/3, 77/81. I would like to record the second derivative test. Let's see be a critical number of a continuous twice differentiable function f. If the second derivative at x equals c is less than 0, then the function has a local maximum at x equals c. Let's see why this is true. If the second derivative is less than 0, then the function is concave down. Only when you concave down, you can have a local maximum. Look at the shape. So if there is a max or min, because the shape of the graph is like that, it has to be a local maximum. Here is the second case. The second derivative is greater than 0. So it has to be concave up. If you look at the shape now, you can see that if there is a local extreme, it has to be a minimum.